Now that we've learned about dihybrids, this allows us to explore another possible outcome of a dihybrid in a cross, and that's the issue of recombination. So if we take two pure lines, say, that differ in the alleles that they carry, this would generate a dihybrid in the F1. If we think about this in terms of input haploid sets of alleles, and haploid simply means the reduction from 2n to n that occurs during meiosis, then it would be fairly straightforward for these two organisms. This organism would pass these alleles in a haploid set, and this organism would pass these alleles. An alternative way to write the genotype of the F1 dihybrid would thus be like this. And this would indicate the two input packets. Now, when this organism goes on to make haploid packets of its own, there are four possible outcomes. The first outcome that we can consider is this one, and at the same time, let's consider this one as well. These two outputs are exactly the same as one of the inputs. If we see this output coming out, then that's exactly the same as that input. These two alleles stayed together as a set and went through the hybrid as a set. Same for this package here. Comes in as a set, these two alleles, exits as a set. So these two would be said to be non-recombinant. On the other hand, there are two other possible output sets of haploid sets. And these are recombinant. And the reason is, these sets are new combinations of alleles. We didn't ever have a little a and a little b together in the parental generation. So as an input, the two inputs there, these two output sets do not match either input. So we would say that these are recombinant. The goal of recombination analysis is simply to determine the frequency of the recombinant gametes. Or more properly, that's gametes if we're talking about a diploid. Or another way to put that more generally would be to say the non-recombinant and recombinant products of meiosis. So the goal of recombinant analysis or recombination analysis is to measure the frequency of the recombinant products of meiosis. We can actually define recombination frequency as simply the proportion, the number of recombinant gametes or products of meiosis out of the total products of meiosis. So the frequency of recombinance is simply the total number of recombinant products of meiosis, haploid outputs, out of the total products of meiosis. One thing that's important to point out at this point is that recombination is strictly defined as new combinations of alleles in output products of meiosis when compared with the input products of meiosis. So it's all about what's going in and then coming out of this dihybrid. We have input sets and then we have output sets. Output sets that differ from either input set are said to be recombinant, and output sets that are identical to one of the inputs are said to be non-recombinant. And again, as we mentioned, the frequency of recombination is simply the number of recombinant products of meiosis divided by the total number of products of meiosis. Now, an important point to make here is that recombination is a genetic event. And when we say genetic, what we mean is there are new combinations of alleles. Now, though, we can start to talk about the different physical processes that give rise, or potentially could give rise, to recombination. And you're probably aware of them. The first we've already encountered to a certain degree, and that is independent assortment of chromosomes. When we did the 9:3 to 3:1 ratio in the dihybrid cross in the previous lectures, that was based on independent assortment, with these different loci, these two gene loci, being on chromosomes that are independent of one another, meaning that they were either on separate chromosomes altogether or far enough apart on the same chromosome that they are acting as if they're assorting independently. The other physical thing that can give rise to recombination is crossing over. So we could have independent assortment of chromosomes, or we could have crossing over. Crossing over is required for recombination of alleles that are on the same chromosome. And in order to represent this, we need to start talking about how meiosis works and how we can represent meiosis, which is what we'll turn to next.